Hello, and welcome to Part 5 of the TI Precision Labs on op-amp stability. The previous videos discussed the concepts involved in basic stability theory, as well as how to test and simulate for stability issues in SPICE and on the bench. This video will discuss why capacitive loads cause stability issues, and will present the first capacitive load compensation technique using an isolation resistor. Part 1 of the stability series discussed that the most common cause of stability issues in amplifier circuits is caused by capacitance on the output. Some common circuits that frequently have large capacitive loads are voltage reference buffers, cable shield drive circuits, and MOSFET drive circuits. In the case of the MOSFET and cable drive circuits, the capacitive load is not always immediately apparent, so be sure to examine if the output is connected to anything with parasitic capacitance. Now that we know how to generate the open loop curves of an op-amp circuit, we can simulate the effects with a capacitive load to determine the issue. As the results show, the 10 nanofarad capacitive load results in a pole in the AOL curve which degrades the loop gain phase to only 4 degrees at FC. Let's examine why this happens. If we take a look at the simplified representation of the open loop circuit, we see that the input signal passes through the AOL block and then the series open loop output impedance, RO, before reaching the op-amp output voltage, VO. When a capacitor, C load, is connected from the output to ground, the op-amp AOL curve is loaded by the RC voltage divider formed by RO and C load. To understand the effects of the output load, the AC transfer function of the equivalent RO plus C load circuit has been plotted here. The pole location can be calculated from the transfer function and is shown at the bottom of the slide. If the original op-amp AOL curve and the AOL load curve are combined, the result is the loaded AOL curve shown on the bottom. The AOL pole from the interaction of RO and C load causes the AOL curve to change to a negative 40 dB per decade slope and reduces the unity gain phase margin. Now that we understand how a capacitive load contributes to circuit instability, we can introduce our first compensation technique, known as the RISO method. The RISO method compensates the circuit by adding a zero to the AOL curve to cancel the pole formed by the output impedance and the capacitive load. Looking at the open loop results from the RISO compensation method, a zero can be seen canceling the pole that was formed from RO and C load. This results in a return to a 20 dB per decade AOL slope and significantly improved phase margin. We can examine the open loop RISO circuit the same way we examine the capacitive load circuit. Once again, the AOL is loaded by an impedance divider, but this time both RISO and C load are on the bottom side of the divider and RO is on the top of the divider. We can compare the AOL load to a classic resistive voltage divider. Remember, the transfer function of a voltage divider is equal to the impedance of the bottom leg divided by the sum of both the top and bottom impedances. The same applies to the circuit with RO, RISO, and C load as shown on the right. RO makes up Z1, the impedance of the top leg, while the series combination of RISO and C load make up Z2, the impedance of the bottom leg. The transfer function can be simplified to the form shown at the bottom right. The numerator shows a zero dependent only on RISO and C load, the two external circuit components. The denominator shows a pole dependent on RO, RISO, and C load. The resulting Laplace transfer function for the AOL load is shown here. Again, with a single S term in both the numerator and denominator, it is clear that there is now both a pole and zero in the transfer function. The equations for the pole and zero frequency are shown here. It's important to note that the zero frequency is only dependent on the two external components, RISO and C load. Plotting the AC transfer function, you can see that the positive phase shift from the zero cancels the negative phase shift from the pole, causing a net phase shift of 0 degrees. Adding the AOL and AOL load curves together as before, we can again see that the zero added by RISO cancels the pole in the AOL curve and restores the unity gain phase margin to an acceptable level for stability. To design the RISO circuit for a phase margin above 60 degrees, first find the frequency where the loaded AOL curve is equal to 20 dB, F0. Then, to calculate the value of RISO, use the equation shown on the left and plug in the values for C load and F0. An RISO value of 108 ohms is the result in this case. Designing with these steps will result in a phase margin between 60 and 90 degrees depending on the op-amp unity gain phase margin and location of the AOL pole. In summary, first find the frequency where the loaded AOL curve equals 20 dB and set the 0 to that frequency by calculating the proper RISO value. If the circuit is not required to deliver large output currents, then consider increasing RISO to be equal to or larger than RO, and the circuit will be stable under basically all capacitive loads. Comparing the transient response of the circuit both with and without RISO compensation, we can see significant improvements by using RISO. Without RISO, the output of the circuit shows heavy overshoot and ringing and takes a long time to settle to the proper value. With RISO, the output has a small controlled overshoot and quickly settles to the proper final value. While the RISO circuit is both simple to implement and design, it has a big disadvantage in precision circuits. The voltage drop across RISO is dependent on the output current and may be significant compared to the desired signal. As shown here, a 10 mV signal has over 3 mV or 30% of error due to the 250 ohm output load. In summary, this video discussed the theory behind why capacitive loads cause stability issues and presented a simple method to compensate the capacitive load by placing a resistor, RISO, between the amplifier output and capacitive load. The next video will present a second capacitive load compensation technique that fixes the DC errors caused by the RISO circuit. Thank you for your time. Please try the quiz to check your understanding of this video's content.